In the Chem Activity 1 of the Organic Chemistry course 212, we will review the concept of Lewis structures. It is worth noting, however, that throughout the course we will typically represent molecules using bond line drawings, not full Lewis structures. But keep in mind that bond line drawings are simply simplifications of Lewis structures. Therefore, in order to work with bond line drawings, we need a fundamental understanding of Lewis structures. Gilbert Lewis developed his model of bonding in the early 1900s, before the quantum mechanical model was conceived. Remarkably, many aspects of Lewis's model are still routinely used by organic chemists today. The model is simple, and yet, in many cases, allows for accurate predictions of chemical reactivity and physical and chemical properties of molecules. Lewis's model focused on the atom's outermost electrons, which can be referred to as valence electrons. Lewis proposed the following representation for the first 10 elements with their valence electrons. Each valence electron is represented by a dot. Please stop the video and consider the key questions 1 and 2. It should be obvious that there's a clear correlation between the column number for the main group elements and the number of valence electrons associated with an atom. Here are the number of bonds that can be made by each atom. While Lewis proposed that there is a connection between the number of valence electrons and the number of bonds an atom can make, you may have found that the connection is not as obvious or clear. For the atoms lithium through to carbon, it appears that a single electron is required to make a bond. With this reasoning, we might have expected that nitrogen would make 5 bonds and oxygen 6 bonds. There is apparently something else at play here. By examining bonding data for hundreds of compounds, Lewis would have picked out some repeating patterns, especially common to the elements carbon, nitrogen, oxygen, and the halogens. To explain the data, Lewis proposed that electrons tend to exist when they're in molecules as pairs, either as a bonding pair or as a non-bonding lone pair. And this is true even though we know electrons repel. Please stop the video and consider the key questions 3 and 4. Here are typical Lewis structures for ammonia, water, and hydrogen fluoride. The lone pair is obvious in ammonia. The dashed lines represent the bonding pair. The same labeling can be applied to the other molecules. It is important to keep in mind that the dashed line in a Lewis structure has a number of meanings. For one, it does represent physically a pair of electrons located between the nuclei of the two atoms. But more symbolically, the dashed line also represents a chemical bond, and as such it represents a mutual attraction by the nuclei of both atoms for that shared pair of electrons. One of the bonding patterns in molecules that Lewis came to notice, and this is hinted at in the key question 4, is that in stable molecules involving carbon, nitrogen, oxygen, and fluorine, the central atom is surrounded by 8 electrons. Lewis concluded that there must be some inherent stabilizing outcome when these octet conditions are met. This would explain to some degree why nitrogen does not make 5 bonds or oxygen 6 bonds, as then an octet could not be achieved. Based on these observations and conclusions, Lewis proposed that any atom, ion, or molecule that can be represented by a legitimate Lewis structure should actually exist in nature or be possible to be made in the laboratory. A legitimate Lewis structure is the line bond representation in which the sum of the electrons around a hydrogen is 2, that would be a bonding pair, and the sum of electrons, both bonding pairs and lone pairs, around a carbon, nitrogen, oxygen, or fluorine is 8, an octet. This corresponds to what we know as the Octet Rule. It is remarkable that a simple pencil and paper exercise can lead to the prediction of the possible existence and properties of a molecule. Before we go on, though, I do want to make a few points. In a later activity, I will clarify what is required in drawing a full Lewis structure versus a bond line drawing, which is not quite the same thing as a line bond representation mentioned here. Next, while you may already be familiar with the so-called Octet Rule, and may believe that it can be universally applied to atoms of most elements, technically it is only truly applied to carbon, nitrogen, oxygen, and fluorine. And that said, while for these elements the octet is never exceeded, we will often encounter examples of carbon having less than an octet, although admittedly it's not very stable under these conditions. Finally, there is nothing in the Lewis model that explains why having an octet for these elements is stabilizing. I will come back to this idea throughout the course. Sometimes more than one legitimate Lewis structure can be drawn for a single molecule or ion. In such cases, with a few additional tools, it should be possible to pick out which structure is a more accurate representation. Consider the following Lewis structures for CO2. Both of these structures are indeed legitimate in that both have octets around all of the atoms, and as we shall see later, they also have the correct number of valence electrons. I will foreshadow that there is something missing on the right-hand representation, but we'll come back to that in a minute. Perhaps some of you will recognize that we've drawn resonance forms of the CO2 molecule. So I refer to two structures, but actually it represents one entity, one carbon dioxide molecule. We will add the double-headed arrow to symbolize this. Note that this is not an equilibrium arrow. The structures do not oscillate from one to the other. Rather, we picture that the actual structure for CO2 is a fusion of both of these representations. Given that the representations, however, are different, there's a good chance that one representation reflects more accurately the true nature of the CO2 molecule. We say that such a structure contributes more to the resonance hybrid. How can we decide which resonance form contributes more? Notice that we're told experimentally we find that both carbon-oxygen bonds in CO2 are identical. I ask you to stop the video then and see if you can apply this information to choose the resonance form that best fits this data. The experimental data points to the fact that the left-hand structure contributes more to the resonance hybrid. You may recall that double and especially triple bonds are shorter than single bonds. If the right-hand structure contributed more to the resonance hybrid, we might expect that the actual molecule has a short carbon-oxygen bond and a long carbon-oxygen bond. Given that the carbon-oxygen bonds are equal on both sides of the carbon, the left-hand resonance form appears to contribute the most. We came upon this decision by having extra experimental data. It would be helpful to be able to make this decision simply in the process of drawing the Lewis structures. We will come back to these structures, but let's look at another example.